Hi, everybody, and welcome back to our next video. So this is actually the last section out of Unit 2, and today's topic is all about related rates. So basically, related rates is just a real-life application of our implicit differentiation process, and we kind of pair that with the rate of change stuff that we were talking about in the last section as far as interpreting real-life quantities and how they change. So by now we hopefully understand that when we use implicit differentiation, we're essentially using all of our same rules except for when we take the derivative of a term that involves a variable different from our variable of differentiation. So again, if I take the derivative of a y variable with respect to x, then we have to do something differently. Again, that's because when we use implicit differentiation, we're always applying the chain rule. Again, when we see a y squared term, we're still following the pattern of a quadratic term, which is a linear pattern to find its derivative. But because the variable y doesn't match up with the variable of differentiation x, that's where we have to apply the chain rule. And that's where we create those extra differential quantities of the dy dx's that popped up in all those implicit differentiation problems. However, when the variable differentiation and the variable in our term do match up, then the chain rule's kind of rendered unnecessary. For example, if I take the derivative of x squared, we know that is 2x based on the power rule, but really I could say that that produces the differential quantity of dx over dx, but they're the same thing, so they equate to 1. That's what Isaac Newton figured out when he discovered this system, is that when those variables match up, this extra piece is not necessary. But when the variables don't match up, y squared still follows a quadratic pattern, which can be represented by a linear expression. That's why we still get 2y. But because we're looking at how this changes with respect to x changing, then we have to apply the chain rule and create the dy dx factor as well. So that is true no matter what the variable of differentiation is going to be, whatever that variable we're taking the derivative with respect to. It could be anything. So when the variables match up, we don't need this extra quantity. When they don't match up, then we do. So what we need to get used to is taking the derivative with respect to other variables besides just x, because x is not always the most important variable that we want to kind of control things with. For example, a lot of the problems that we're going to look at today revolve around how certain real life quantities change with respect to time. So time is going to be the controlling variable. So for these three examples here, we're going to take a look at how quantities change with respect to t, or it's really going to represent time. So again, same rules apply though. If the variables match up, so if I take the derivative of a quantity of time with respect to time, then it's just based on whatever kind of pattern it follows. So again, power rule. But if we try to take the derivative of any other kind of variable, now it's going to produce some kind of differential quantity like dy dx, or in this case, a dr dt. So r cubed is still just like x cubed would be 3x squared, r cubed is 3r squared, but we have to apply the chain rule. So the derivative of r with respect to t would produce dr dt. So we just have to get comfortable with seeing these quantities without the y and x in there and some other kind of variable. And then for the second guy, t squared with respect to t still would just be plus 2t. Or if I tried to take the derivative of sine of 3r, this would be a chain rule. We've got an argument of 3r. And since r and t don't match up, u prime would still just be 3, just like 3x turns into 3. But now we would also have the dr dt quantity. So then when I take the derivative with respect to time of sine of u, that gives me cosine of u times u prime, or 3 cosine of 3r times dr dt. So it's a very familiar process. Again, we just really have to reiterate over and over again that we are really working with the chain rule, similar to how we did with the implicit differentiation. All right, so to begin our discussion of related rates, basically we're going to be looking at a whole bunch of real life situations. And instead of dealing with just the y and x variables, again, we're going to be dealing with formulas that represent these real life quantities. And then we're going to be taking a look at how those things change with respect to time. So it involves a lot of implicit differentiation, but we're also going to be working with equations that we probably haven't come across anytime recently. So we want to kind of recap some of that stuff as we go. But to get us started, let's say, for example, we fill this cone up with water and we want to measure how fast the water drains out of that cone. So when we talk about how fast something occurs, that in and of itself is talking about how a quantity is changing as time changes. So we're talking about a rate of change. So if the volume depends on certain parts, that means the rate of change for the volume also depends on those parts. So when we talk about how much water is in the cone, that's talking about volume. And for a cone, there's a formula for that. And if you don't remember, that formula is volume equals pi over 3 times r squared h. So now let's talk about what the question's actually asking us to do. So we want to find the rate of change of the volume of this cone at any given time. Well, what's a little confusing at first when we first get started with these related rates problems, the quantity of time doesn't actually show up in the formulas that we work with. And that's because time is not something that the volume actually depends on when we calculate it for a given moment of time. What it actually depends on are these other variables. So when we think of the relationship between volume and time, well, it depends on at a given moment in time, what is the radius of the cone? What is the radius of the height? So if you think about the quantities that actually um, the real life quantities actually depend on, those are the really important ones, and those are the ones that are going to play the important role in the calculus process. So where time is going to show up is if we want to know how it's changing at a given moment in time, that is describing to us our variable of differentiation. So instead of taking the derivative of these equations with respect to x or r or h or v, all of these problems we are going to take the derivative of with respect to time. So we are going to ddt this formula. And what that does is it forces time to now be a part of the problem. So now we are going to produce a whole bunch of extra quantities because if you look at it, there are three unknown quantities in this formula: the volume, radius, and height. And none of those match up with the variable of differentiation, which means it's going to produce three differential quantities in this derivative equation. So let's go ahead and actually do the math here, and then I'll explain how we're going to end up trying to work with this. So the derivative with respect to time of volume, that is just simply dv dt. Or another way of thinking of it is it would be 1 times dv dt, but we don't need to write the 1 in there all the time. Then on the other side, pi over 3 times r squared times h. That is a product rule. Now remember, pi over 3, that's just a coefficient. It's a constant multiple. So I'm going to group that with the r squared. So if that's my first function, then I would get 2 pi over 3 r. But because r doesn't match up with t, that also produces a dr dt. Then second factor would be h, and that would be 1, but again, variables don't match up, so we get 1 dh dt. And again, just like with v, I don't need that 1 in front. I can just treat it as dh dt. So product rule, insides minus outs, or excuse me, plus outsides. So I end up with 2 pi over 3 rh times dr dt plus my outsides would produce pi over 3 r squared times dh dt. So that is a mouthful. But if we look at this equation, what this is really kind of telling us is the rate at which the volume of the cone is changing depends on a whole lot of information. If I wanted to finish this problem and know exactly the value of dV/dt or the exact rate of change that this volume is increasing or decreasing at a given moment in time, I'd have to know values for all of the unknown quantities in this equation. And if we were to list them, we would need to know our radius at a given moment in time. Then I'd also have to know the height of the cone at a given moment in time. Again, I need to know r over here, but then we also have to know these rates of change. I'd also have to know how is the radius changing at that given moment in time, because that will have an impact on how the volume's changing. And then same thing for the change in the height. So what what happens here when we are working with these real life quantities, we have to know certain information in order for us to actually be able to calculate the things that we're looking for. The calculus part is kind of its own thing. Again, it's just implicit differentiation with the chain rule, with these different formulas. That part is easy to wrap your head around. What's a little bit trickier sometimes is realizing how all of these different things contribute into this one quantity. And that's where we have to come up with some strategies to help us. And with cones, there's an important relationship that is always in existence with any, how we refer to it as a right cone. So a right cone, or again, it comes from a cone is actually a portion of a right cylinder. So a right cylinder is a cylinder whose height is perpendicular to the radius of the base or the diameter of the base. So think of it like a soup can rather than like the Leaning Tower of Pisa. There are cylinders that look like this because it's still circles stacked on top of each other, but the uh, the angle is kind of slightly tilted. But when we have a right cylinder, if I cut out the inside part of it, it creates a right cone. And when that is the case, you guys have a special relationship. So what's really going on in this cone right now is it's filled. So again, we fill this cup or this cone up with water, and then we're going to cut a hole in the bottom and it's going to drain out. So as it drains out, the level of the water is going to decrease. And you can see in these subsequent pictures, the cone of water sitting inside the cup, it still holds its shape, but it's going to be a smaller and smaller cone as the water leaks. Or, in other words, if we think about this, as time passes, the volume of water still in the cone has to be decreasing. So I know that dV dt is going to be negative. What also is decreasing is the size of the circle on top. So that means the radius is shrinking. So dr dt would have to be a negative number. And the height of the water is also decreasing. So that would have to be a negative number. So there's lots of pieces of information in the situation that's going on. So all of those rates, again, play a role. But what doesn't change is as that circle or the cone shrinks in size, there is a special relationship that is always held to be true in how the size of the radius compares to the size of the height. And that's because of the idea of similar triangles. So if you remember, similar triangles are said to be proportional to one another. So for example, if I were to take the radius at the start divided by the radius or excuse me, divided by the height at the start, and I were to compare that to the radius and the height at each one of these subsequent stages, they are actually proportional to each other, or means the ratio of the original R over H, so let's call that R1 over H1, has to be equal to R2 over H2. Another way of saying that is that when they are proportional, there is some kind of constant that ratio is equal to. So we can say that R over H is equal to some number. Because of that special relationship with these cones, we can actually turn what is a very complicated problem that requires us to know 4 pieces of information into a much simpler problem. Because what I'm able to do is solve for one of these variables. So let's say that I multiplied both sides by h. That means that as long as I know the original radius and height, I can actually calculate the radius at any moment in time based on this relationship because of this k value. As long as I know one piece of information, so as long as I know the height, I can just multiply by that constant and it will calculate for me my r value or my radius. So what that allows us to do is it allows us to go in at the beginning of this problem and actually rewrite it all in terms of r or h, depending on the situation. So there are special strategies when it comes to these cone problems. So what I'd like to do is let's give an actual scenario here. So let's turn this into a more specific problem. So the way that these problems are typically going to be structured, again, another special name for related rates is find when given. So we call them that because typically the way these problems are going to be structured is I'm going to ask you to find a quantity. So in this case, I'm going to ask you to find the rate of change of volume with respect to time when a certain piece of information is true. So let's say when our radius is, let's say 3. Given that this last piece has to be some kind of rate of change piece of information that is required for us to actually calculate the desired value. So again, going back to this original setup, that's like something out of this box. So if I really want to be able to calculate the change in volume, I have to be told one of these rates of change. So let's say that I tell you dr dt is equal to -2 cubic inches, or excuse me, not cubic, -2 inches per minute. Okay. So notice the units there. This is a rate of change, and that's because dr dt is a rate of change. So I have to have units for however my radius is being measured over whatever units my time is being measured in. So if I give you those 3 pieces of information, we actually have everything we need to go about this problem. Now, the only thing that's actually missing is instead of just unknown values for the original radius and height, we're going to have to pick some numbers. So let's say that, I'm going to make some space here. Let's say that the original cone, when the cup is actually filled all the way up, has a radius of 5 and a height of 10. So what that tells me right off the bat, my ratio for R over H is always going to be 5 over 10, or another way of saying that is my rate. There's actually 2 other ways to say this, depending on which one we want to solve for. So I could then say that my radius is equal to half of my height at all times, or I could say that my height is actually twice the radius at all times. Which one of these forms we use depends on the information that is given to us. So because I am given a value of R and a value of dr dt, we actually want to use the second one. I want to actually replace anything that has H in the original equation in terms of R. And that's because if I don't make this change, then I would be given a value for R, so that satisfies that part, and dr dt. But there wouldn't be any way for us to come up with the H in the dH dt without having to do some extra calculus. What's easier is I can actually go to the original form and substitute this in and turn this into an expression of all R values. So rather than it depending on all 4 of these, we can actually replace 2 of them. So that's going to be my first thing here. So there are some instances where we can rewrite the original function in a different format that makes the calculus a little bit easier. So the only way we get to do that is if it's something that is true throughout the entire process. So we wouldn't be able to stick a value in here for H because the height is not always the same thing as we go through this process. Again, as the water drains, the height's changing. But this relationship between H and R is true the entire time. That's what allows us to substitute or make this exchange here at the beginning. So let's go ahead and do that. So again, I'm going to replace my H with 2R. So my new expression is pi over 3 R squared times 2R, or volume is equal to 2 pi over 3 R cubed. Again, what we just did was we took an equation that said volume actually depended on 2 variables, or dV dt would depend on 4 quantities. And now we've made it much simpler, and it just depends on R. So dV dt only depends on 2 items. So now we can take the derivative. So now we are going to take the derivative with respect to time. And that results in dV dt equals, bring down the 3, so I end up with 2 pi R squared times dr dt. Again, applying that chain rule, variables don't match up, produces that differential quantity. So again, notice that this derivative is way easier than this previous guy. And again, that is a special thing that happens when we do these cone problems. It's specific to cone problems because they have this special similar right triangles feature to their shape. There's not really any other shape that we work with that deals with this. So this is special only for these cone problems. But now I have an equation that has an R value that I can substitute in and a drdt value. So sometimes when we're doing these, you just have to make sure that we have everything that we need that we can do our substitutions, okay? So I want to find dVdt. It's already isolated. I don't need to move anything around, but now I can make these substitutions. So we get 2 pi times 3 squared times -2, or negative, and I multiply all this together, 36 pi. So negative 36 pi is the quantity for dVdt, or the value of dVdt. So volume, remember, is a cubic dimension. So length times width times height, however you want to describe it. We are trying to calculate the dimensions for this. Each linear dimension is going to be used for using inches. So then our units for dVdt would be inches cubed, but again, it's a rate of change. So inches cubed is the volume units, and then that would be per minute. And we could get a decimal value for this if we wanted to. So 36 pi would be 113.097 inches cubed per minute. So again, that kind of lines up with what we talked about before. As the water drains out of that cone, we knew that this volume was supposed to have a negative rate of change. Otherwise, it would have been describing that there was water being added to the cone, and we know that is not true. So this is the typical process of these problems. Again, this little exploration, the goal was really just to help you guys understand that sometimes, again, specifically with cones, when we know the size of that radius and height to begin with, when the cone is in its full big shape, we can use that special relationship to turn this into a much simpler calculus problem rather than having to worry about all these extra quantities. So not every related rates problem is going to be this difficult with all the extra rewriting and stuff. It's really just cones that we have to kind of treat specially. But what is going to be similar to all of these is every single one of these find when given problems, we are going to start with an original quantity. We are going to identify what quantity we want to find when a certain condition is true, given that a particular rate of change is known. Once I have all that information, then we do our calculus, then we plug in the values we know and try to evaluate for the one that is missing. So let's try another one here. So this one's a much simpler problem, but a pebble is dropped into a calm pond, causing ripples in the form of concentric circles. So concentric means they all share the same center. So I've got a small circle to start, and then a bigger one and a bigger one, but they're all orienting out, oriented out from the same center. So the radius r of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? So basically, we've got little circle, bigger circle, and so on. And we want to know, how is the area of that outermost circle changing as the ripples expand? So the hardest part about some of these is identifying what formula or equation to start with. But it's almost always going to be related around how all the different various pieces of information kind of come together. So the different quantities that were referenced here were the radius of a circle and the area of a circle. So you kind of have to think about what kind of equation or formula relates all of those together. And a lot of times it can be kind of obvious. So in this case, there is an area formula for circles. We know that A equals pi r squared. So that accounts for all of the different quantities that were given to us. So that is our starting equation. But now we want to set up our find when given information. I highly recommend that you guys set your problems up like this. It helps organize all the information given to you. So we want to find the rate at which the total area is changing. So dA dt. And sometimes it's helpful to think about the context of the problem as whether or not that quantity is going to be positive or negative. So if you think about what we know the circles are rippling outward, which means the next circle is going to be bigger than the last, which means more area. So we know that the area is increasing, which means this guy should be a positive number. That's a nice, easy way to check yourself, because if you miss a negative or forget to cancel something out, it's easy to mess up the sign of these complicated problems. But if you think about that ahead of time, it's an easy way to check yourself. So that's a quantity we're looking for. The when condition is something about the one of the values that we have to substitute in, and it will typically say when something is true. So in this case, when our radius is 4. Given that some other rate of change is known. So we're told that the radius is increasing at a constant rate of 1 foot per second. So that would be the quantity of dr dt. And because it's increasing, we know it's positive 1 foot per second. So let's get some units out there. So if the radius is using units of feet, time is using unit of seconds, then dA dt, we know, because it's area, that's the second dimension, will be feet squared per second, or square foot per second. All right, so we have all the information identified. Now we can do our calculus. Again, this one has nothing to be plugged in at the beginning, because there's nothing about this situation that will remain constant. So the radius isn't staying the same, the area is not staying the same, and those are the only two quantities in here. So again, another way that this is different from the cone problem. But we've got ddt of A, that would produce dA dt. Pi r squared, I know it may be tempting to treat this like a product rule, but this is not. Pi is just a constant multiple. So we just get 2 pi r, but then times dr dt. And because we're looking for dA dt, it's already isolated. Which rate of change we're solving for is going to change from one problem to the next. So there will be some times where we need to isolate a rate of change that is with other stuff. But for this one, dA dt is already isolated, so we don't have to worry about that. But now that we've done the calculus, now we can substitute in values for a specific moment in time. So there is some moment, if you were watching this on a camera or with your phone, and you snapped a snapshot of one single moment in time when the radius is 4. So that is one moment in time that we can plug that in. And at that moment in time, it's also known that the rate of change of the radius is 1 foot per second. So we can plug that in as well. So we end up getting 8 pi, or if we calculate 8 pi, we get 25.133. And again, our units here would be feet squared per second. So that is every second that passes, the area of those circles are growing by 25.133 square feet. All right, so if we take a look at our next one here, this one says air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. So a couple of vocabulary things to be on the lookout here for. So the fact that this says this is a rate tells me that it's either, or it's my given content. So again, when we're looking for find when given, find is going to be some kind of rate that we're looking for. The when condition is going to be the kind of input variable values that we are going to substitute after we take the derivative. And then the given is always an additional piece of rate information that they give us. So we know that this is going to be the the change of something, so d something. And then the fact that it's cubic feet per minute, remember any third dimensional measurement is a measure of volume. So dV dt in this case, and if the air is being pumped into it, then we know this is a positive rate of change, so 4.5 cubic feet per minute. And then we want to know what the rate of change of the radius is. So we want to know dr dt. So one thing to keep in mind, though, if I know that the balloon is getting pumped up, then that's why the volume is increasing. But if the volume is increasing, so is the radius. So as the balloon gets bigger, so dr dt, I know this has to be greater than 0, otherwise I did the problem wrong. And then as far as units go, we take the third dimensional units from volume and we just strip away the cube part. So this is some positive number of feet per minute. So just important to always keep the units in mind. But I want to find that rate of change of the radius when the radius is 2 feet. So at that exact moment when the radius is 2 feet, at that exact moment, I want to know how the radius is changing. So remember, I have to come up with my equation that it relates all of these values or variables together. So this one's pretty straightforward. This is volume of a sphere, which if you don't have memorized, that's okay. Usually the important formulas you guys can look up, or they'll be given to you. But that is the equation that we're going to start with. Again, it's always important, though, when you guys start to ask yourself, are there any values in that formula that remain constant throughout the entire process? Because if they do, then you're allowed to substitute those values in at the start of this before we do the calculus, because that will make the calculus a lot easier. But there's not always a guarantee that some quantity will stay constant. Like in this case, your volume is going to change and your radius is going to change. But again, every problem, it's still good to ask yourself that question just to make sure that you've thought about it and you didn't miss anything. But in this case, we don't have any constants, so we will ddt this volume equation. So doing so results in dv dt is equal to, now remember this is not a product, this is all just a bunch of constant multiples in front. This is really just the power rule and chain rule. So bring down to 3, we end up with 4 pi. The 3's will cancel out. And then r squared is my new power, but then again, r and t don't match up. So we have our differential, our rate. So now we can plug in the stuff we know. I know dv dt is 4.5. And then that is equal to 4 pi r is 2, so 2 squared gives me another factor of 4. And then we are trying to find what dr dt is equal to. So now it's just a matter of dividing out these coefficients. So I'm going to divide both sides by 16 pi. And a lot of these related rates problems you guys are going to need to get decimals for. But so we end up with dr dt is equal to 4.5 divided by 16 pi. Now, do be careful when you guys go to type this part into your calculator. The calculator does not read pi as just a come along kind of factor. It acts like a special thing. So you do need to make sure that we have parentheses around that denominator when you type that into the calculator. So what we end up with here is 0.0895. So we're just going to round that to 0.90. And then remember our units from earlier would be feet per minute. So it doesn't seem like the radius is going to be growing all that much. 0.090 feet. That's not very big. It's like a tenth, a little bit less than a tenth of a foot. So it's about an inch every minute. So it's not getting real big real fast. But that is our final answer. Okay. All right. Let's try our next one here. So this one's we coined this the ladder problem. This is a very popular kind of problem. It has a similar structure. You see these quite often. Wouldn't be surprised if you guys see one like this on a quiz or test. It says, though, a ladder 25 feet long is leaning against the wall of a house. The base of the ladder is being pulled away from the house. Here's my house. Here is my ladder. So it's leaning up against the house. And they said that the ladder is 25 feet long. And that's important to note. The ladder is not changing in this process. The length of the ladder is not changing. So that is a constant value. So let's keep that in mind. But the ladder is leaning up against the house. The base of the ladder is pulled away from the wall at a rate of 2 feet per second. So that distance right there, or that point, is going to be pulled away from the house at a rate of 2 feet per second. How fast is the top of the ladder, so this point, moving down the wall when its base is 7 feet, 15 feet, or 24 feet from the wall? So this is like 3 problems, but we're going to kind of mix it together here, okay? So let's start first with the 7 feet option, okay? So my goal is to find this rate of change. But notice there's not really any quantities or variables really mentioned in this problem. So we kind of have to label this with some variables. So in the problem, we know this ladder is 25 feet. And because it's leaning up against a house, we're assuming the contractors did their job and didn't build a leaning house. So it's safe for us to assume that this wall is perpendicular to the ground, which then makes this into a right triangle. So that means we can label this horizontal side something. So I'm just going to use X, and the vertical side something. I'm just going to use Y. Don't have to use those. It's just easy options. So once you label those side lengths as x and y, though, now we can identify our find when given. Because my goal now is to find how the height of this side, or this length y, is changing. So that would be dy dt. And just from kind of looking at the picture and understanding what's going on, as we pull the bottom out, y, that height, the top of the ladder is going to get closer to the ground, or the size of y is shrinking. So I know that this has to be some kind of negative rate. So again, easy way to check ourselves. When, in this case, we're going to start with the base being 7 feet from the wall. So when x is 7. Given that the ladder, the base of the ladder is being pulled away from the wall at a rate of 2 feet per second. So that actually means the size of x is increasing. So dx dt would be positive 2 feet per second. Okay? So again, now I have to think of some formula, some equation, or property that equates all of this information. And well, the easiest choice here, there's a right triangle, and I'm worried about the side length. So our Pythagorean theorem is our go-to. So our leg squared plus the other leg squared equals the hypotenuse squared. And again, this 25 is a constant, which means that number can be used before the calculus. All of this stuff, any of the find when given information, I can't use it until after the calculus is done because it's all representative of a single moment in time, which requires calculus. So this is my initial equation. That's what we're going to start with. And now we can ddt that. So I end up with 2x times dx dt plus 2y dy dt equals, I didn't simplify 25 squared because I know it's just a number and the derivative of a number is just going to turn into 0. So there's not really any point simplifying that because it's going to disappear. But now we've done the calculus. Now I can substitute in the values that we know about. So I know that x is 7, dx dt is 2. But then for the y stuff, I don't have a y value or a dy dt value written down, which means as of right now, I can't actually finish this problem because I can't solve for two variables at the same time. However, when the given moment passes or occurs that x equals 7, in that given instance, this creates a particular right triangle where the hypotenuse is 25 and this bottom side is 7. So when that is, and I definitely didn't draw that to scale, but when that happens, y has a known value, or we can find that value. So sometimes the when information will actually imply some other information that we need to find and know to actually solve the problem. So that's the case here. So what I'm going to do is off to the side do a separate Pythagorean theorem problem to figure out what is the height of the ladder when the base is 7 feet from the wall. Now, if you know your Pythagorean triples, then you know that 7, 24, 25 is one of them. So when I do all this math, 625 minus 49 is 576, and the square root of 576 is 24. So when x equals 7, y equals 24. That's a special instance. So because of that, now I can actually finish this. I can plug 24 in here for y. dy dt is still unknown. So I'm going to move the 28 here over to the other side and then divide by 48. So what I end up getting is negative 28 divided by 48, and then I can reduce that. Or in this case, let's go ahead and get a decimal. It's not going to reduce out all that nice anyways. So we get negative 0.583 feet per second. And again, the sign of that matches up with what we expected because the bottom of the ladder goes out, top of the ladder comes down. All right, so that was for when x is 7 feet. If x is 15 feet, then it's kind of a, the find and the given parts are not changing, but what is changing is the when condition. So now it's when x is 15. So when x is 15, that means the y value is going to change. But again, it's still the same kind of deal. If I give you an x value, you should be able to find the y. So if we do another Pythagorean theorem here, we'd have 15 squared plus some y squared equals the same hypotenuse squared, 25. This is actually another Pythagorean triple. If you guys remember, 3, 4, 5 is the first triple that you have to learn, and any multiple of those also creates a new one. So if I multiply all of them by 5, I get 15 and 25 for the short and long sides. So 20 has to be the missing leg. So that would be my unknown y value. So all this means is I don't have to start the problem all over again because I didn't change the initial equation. So the constants didn't change, the relationship didn't change, and the calculus wouldn't change then. All that's really changing are the values that are substituted into this derivative equation. So I'm really just changing this line. So, or excuse me, this line after we make the substitutes. So all I'm doing here is plugging in these new values. So I'm really going to end up with 2 times 15, still the same rate of change for x, so times 2, plus 2 times the new y value, 20, times dy dt equals 0. So now it's kind of the same idea. I'm going to take, this is really the value of 60. I'm going to move that over, divide by 40. So in this case, my dy dt would be negative 60 over 40, or negative 1.5 feet per second. Okay. Now for the third one, if you think about it, if I make x equal to 24, well, that's actually using the same triple as we used before. The only difference now is these are kind of flip-flopping spots. So when I go to substitute them in, it's going to produce a new value. So I'm just going to, let me choose a different color here, make it a little bit easier. So for this line, we are operating under the idea that x equals 24, which implies that y is 7. So in that case, we would get 2 times x, 24, times still the same dx dt, 2, plus 2 times the y, which is now 7, times the unknown dy dt equals 0. So then same idea, I'm going to take the constant term here. This is really 96, and subtract it. So we get negative 96 divided by the coefficient here, 14, which is going to give us a decimal value of negative 6.857 feet per second. I'm not going to be able to fit the units in there all that well. But the reason why they asked you to do 3 of these is to get you kind of understanding what's going on. Essentially, what happened was we gave you 3 different points in time to look at. So when we started, x was 7 and y was 24. The next time your ladder had actually moved down, now y was only 20. And then at the very end, now y is only 7. And if you notice what happened, we went from a small negative number, so close to 0, to a bigger negative number, further from 0, and then even further. So what this is trying to hint at or express to you is that the top of this ladder is actually speeding up as it drifts down that wall. So again, these change in y over change in t rates, if you look at the units feet per second, that is a measure of speed or velocity. And because we have the negative sign, we actually interpret it as velocity. So this is actually kind of evidence to show that the effect of gravity is taking over here, and this ladder is actually speeding up. The top of that ladder is speeding up as the ladder drifts down that wall, or as we pull the base out from the ladder. So not every one of those ladder problems has 3 different conditions, but that's just kind of the idea that we want to express, and we can show that by looking at various when conditions. Because again, these whens, we are thinking about different moments in time, but because we don't have an input of time here, we control that by giving different conditions for our input variables. All right, for our last example, this is another cone problem. This one says a conical cup is 4 centimeters across and 6 centimeters deep. So we don't have a picture yet, so let's go ahead and try to sketch one. And no, your pictures won't be graded, so don't worry if you're a terrible artist like I am. But you do need to be very careful with our cone problem. Sometimes you're going to be given information about the diameter of the base. Sometimes it's the radius. but remember that the special connection, special relationship is always between the radius and the height. Obviously, diameter has one, but you'd have to convert it if you want to set the problem up that way. But it's easier to work with the radius and the height. So while the diameter of this cup is 4 centimeters, the radius is only 2. So 2 and 2, and then the height whole way across or a whole way down is 6 centimeters. So again, what that means, even before reading the rest of the problem and setting up all of the find when given stuff, we can establish this relationship that R over H would be equal to 2 over 6. Obviously, we can reduce that to 1/3, but we don't really need to transform it just yet because how we transform it will depend on the rate that we have. So if the problem gives me a rate for dr dt, then I want this equation to say H equals something because that allows me to rewrite the volume equation all in terms of R. If I'm given a rate for dH dt, then we'll do the opposite. We'll solve the equation so that it's R equals something in terms of H. Then we can put the H stuff into the equation. So how we transform this relationship is all dependent upon the information that the problem tells us. So it says water leaks out the bottom. So we're assuming that the cup is full to start, and then water's leaking out at the bottom at a rate of 2 centimeters cubed per second. So sorry, I know that's covered up, but 2 centimeters cubed per second, that is because of the units involved, that is them telling us a value for dV dt. So that is actually our given information. Sorry, my pen is not working great. So dV dt is, now, obviously we know centimeters cubed tells us volume, but then we have to interpret the sign of this value. Even if it's just written as a positive, you can't just assume that the quantity is changing in a positive way. Always interpret it based on the context. So if water is leaking out, that means the total volume in the cup is decreasing. So dV dt will be negative 2 centimeters cubed per second. Always interpret the sign based on the context of the problem. So we want to know how fast is the water level dropping. So that is describing the height. So we are looking for dH dt, which again, just to kind of brainstorm, if the volume is decreasing, the water level has to be dropping. So we need this to be a negative number, and that's a way that we can check ourselves. And we want to find that value when the height of the water is 3 centimeters. So if the height, sorry, I forgot the H. If the height is being measured in centimeters, then dH dt will be some number of centimeters per second. So those are the units for our final answer. Then again, we need a formula that puts all of this information together. So remember that the volume formula for a cone is it's 1/3 of the volume of a cylinder. So that is pi over 3 times r squared h. Again, before we do calculus, if I do calculus right now, it requires a product rule. And then I'll have dr dt and dH dt in there. And I don't know all of those, so I don't want all of those. This is where that special relationship comes into play. I know dV dt, so V can stick around, and I want to know dH dt, so H can stick around. So that means I need to replace R with something, so I have to solve this equation for R. So to do that, I just multiply both sides by H, so I get 1/3 H. Or another way of saying that is at any point in time, as this water is leaking, if you know what the height is, the radius is 1/3 of whatever that value is. So that's how we can replace this. So I'm going to rewrite the original. Again, I'm not doing any calculus yet. This would be pi over 3 times 1/3 h squared times h. Or if I simplify that, I would end up with pi over 27, because 3 times 9, times h squared times h, or h cubed. So it takes what would have been a really complicated product rule with the chain rule and basically just turns it into a pretty simple power rule. But now we are ready to DDT this. And that gives us dV dt equals, bring down the 3, so 3/27 reduces to pi over 9, h squared, and then times dH dt. And now we're going to fill in the values that we know, give myself a little room. So I know dV is -2, and that's equal to pi over 9 times h is 3, so 3 squared. dH dt is the unknown. And now when I go to simplify this, 3 squared is 9, so the 9's here are going to cancel each other out. So in this case, all I actually have to divide by is just simply pi. So let's get a decimal value for that. It's going to be a little bit less than 0.6-ish. So, excuse me, a little bit more. So we get negative 0.637. And again, we're measuring in centimeters per second. And again, notice that this value is negative, just like we wanted it to be. That's a way that we can kind of make sure that we didn't end up losing a negative or move something to the wrong side or forget to move something. As long as those signs match up, we will tend to be moving in the right direction. So that is our final answer. So as water is leaking out of this cup every second that passes, or excuse me, at the time when the height is 3 centimeters, at exactly that time, we know the height is decreasing 0.637 centimeters per second. So for all of these problems, you guys are going to practice a whole bunch of different kinds of scenarios with these related rates. But I can't stress enough the find when given setup. So for each one, you're going to want some kind of diagram, some kind of picture to describe all the information that's given to you in the problem. Once you have that diagram set up, label everything. Then identify your find when given information. Again, find is going to be some kind of rate of change we're looking for. When is some kind of condition for the input variables. And then our given is going to be some other rate of change that is relevant to the situation. Then we're going to try and find some kind of formula or equation that relates all of the quantities given to us in the problem together. Once we have that initial equation, remember to always check for constant values. If anything is constant, or if there is some kind of special relationship, mainly with these cone problems, that kind of information can be plugged into the initial equation before we do the calculus. That's to make our calculus part easier for us. That's why we did this here with this cone problem. Then we do our calculus, and then we can substitute our when and given information to find that missing value. So these all follow a very similar process. Really, the only difference from one problem to the next is how all the given information relates and what initial equation we're going to set up. So best of luck, and let me know if you guys have any questions.